All right, so this is still section 3, lecture 17, NaiveBC classifier for the text classification. We're in the module 2. So in this module, I will explain multivariate Bernoulli and multinomial model NaiveBC classifier and how use the first multivariate Bernoulli to perform classification, text classification on background words representation. How do you do the performing in the testing phase? How do you learn the parameters in the training phase? So essentially, the parameters are just a conditional probability and of words condition on each class. So let's get started.
Oh, but I want to get a really careful discussion and hopefully to help you to finish the homework nicely and also got a deeper understanding about handling this kind of data. So there are two different probabilistic models. One is called multivariate Bernoulli and the other called multinomial. So what do I mean multivariate Bernoulli? So the equation on the bottom is the equation we need to use, right, in the generative base classifier. And if we want to use generative base classifier, so let me just, again, using our notations, still CI, and then I'm converting, just using D to represent as a document. For a specific document, I just converted, it's the same PCI times PD condition on CI, so this is the one I need to estimate for a specific document D. Then how do you represent this? Because we always know how to represent PCI, right? That prior probability, which is very easy to estimate. It's just a count of a specific class over all the possible occurrence. So there are two different ways you're representing this, which is related to the background word representation we just reviewed. You either represent this as probability. So this is if you're representing it as count, this is a count-based formulation. And then if you're representing it as a Bernoulli, and this is the Bernoulli, you need to figure out how to represent it, right? So the first kind, which is exactly, if you use the naive assumption, which is exactly the multivariate Bernoulli distribution. We're using a multivariate Bernoulli distribution to represent this joint conditional formulation. For the second kind, we're using multinomial distribution to calculate the second kind. Okay, so then what is this? So I'm going to talk about what are they after a few slides. So first, let's compare. So multinomial versus multivariate Bernoulli, so why, based on the 1997 until 2005, there are actually a lot of papers compare this. The multinomial model is almost always more effective in the text applications. So this maybe sounds so trivial, right? But you need to think about maybe in the future, you have some kind of discrete type of features. Consider maybe use the counts. This is not just to text, right? Consider use the count, not just use exist or not. So especially in a lot of system or security type of formulation, actually people use this multivariate Bernoulli model a lot. Is this PDF comment section that exists in my PDF documents or not? Or there are actually a lot of those type of models even now in a lot of domains. Yeah. All right, so it's actually from Chris Manning. They compared, and the comparison it's on this quite simple toy task. So for a university homepage, you want to classify it as student, faculty, and other things. And it just hand crowd 5,000 hand-labeled web pages from Cornell, Washington, UT Austin, and Wisconsin as a training, and you apply and crowd classify as from the sites from current and Allen. And so this is the figure they compare. So actually, it depends on the vocabulary size. When your vocabulary size is pretty small, actually multivariate Bernoulli is better. When your vocabulary size is kind of larger and larger, in this case is 100K. Yeah. So even though we have only 5,000 training data, but actually the dictionary size here is huge, right? Dictionary size is 100K. And this is very classic for text classification used to. It's a huge, high-dimensional task. All right, so now let's see what is multivariate Bernoulli, which you already learned. It's exactly naive-based classifier, and each entry is a Bernoulli variable. So now we have this Bernoulli vector, and each entry shows a Bernoulli variable, exist or not exist. And then you're trying to representing this joint vector condition on each class labels, right? So first, let's see the assumption this representation making. The whole assumption is one word in the document tells us nothing about chances that another word appears. The naive, we're going to use a naive-based assumption to decompose this joint probability into multiple conditional probability. So we're going to so this is the model. The naive assumption here actually means one word appearing in my document tells me nothing about another word appears in the document, which is actually apparently not very good, right? Yeah. All right, but that's all you can do, right? Because otherwise, how can you even estimate? This is exactly what we had in that tennis example, right? You need to have all the possible combinations, which is 2 to the p, and to count each case inside the 2 to the p from your training data. There's no way. Like, just let's again see the size. Labels is about 10,000, p is about 100,000. 2 to the 100,000. There's no way to estimate that. You have to convert this into, because this is one of the question, right? If I'm doing naive, how many parameters do I need to estimate? Assuming there are only two classes.
2p.
2p, right? So in this case, 2p is how many parameters? Assuming p equals to 100K. 2p is 200K. And then how many samples do you even have? 5,000, which is still pretty short if you think about it. And we need to make assumption to extremely simplify. Just the reason is the space is super large. All right, so you do conditional independence assumption. This equivalent to this multivariate model be decomposed into p independent Bernoulli variables. And then this is exactly what we showed in the naive-based classifier. You can use a graphical model representation using the class label as the parent. Every every features is a children node in this representation. And then the joint conditional probability becomes the multiplication of each marginal conditional probability. All right, so how do you estimate each P1 equal to true condition on C or PW whatever W, right? PWI condition on CJ. So this is because of Bernoulli, right? And as long as you know P hat and it's enough to know the Bernoulli distribution, and then you need to estimate PWI condition on CJ, J from I from all the vocabulary words, and J is from 1 to all the L classes. So we actually had all talked about this already because and this is the matrix you're going to estimate. It's a matrix with I use K here. It's actually just the vocabulary size. Yeah, and just use K to represent vocabulary size, and then it's a matrix. This is your model. This is the model you estimate from data. All right, so I'm not going to cover this, but I hope you can read this. Is how to estimate Bernoulli variables parameter p hat, and the whole idea is maximal likelihood estimation, and assuming just you observe hat, and then to the tail. And then you're representing each observed data through this formulation, P to the specific, if is it head or is it tail? And because you're observing n of those, right? Then you just multiply, so your likelihood is multiplication from the first observation onto the nth observation. For each observation, that's the probability through that, through this Bernoulli probability formulation. And this formulation can be easily converted, so because this is a multiplication, right? And all this under the power, they are all P, and this becomes what? P to the summation of xi, and 1 times P to the summation of 1 minus xi. Right? It just, for all the observations, you observe x1, x2 until xn, they are head, tail, or you convert them into 1, 0 form. And each one of them has this, and then because multiplication is equivalent to P to the summation of xi times 1 minus P to the summation of power of summation of 1 minus xi. And because for those xi equals to 1, this is what? Summation of xi, because xi is this representation, right? Xi means if its head is 1, if its head is 1, if its tail is 0. So summation of xi is what? It's the number of times heads appeared in that n trial. All right. So this is the likelihood. The likelihood is P to the number of times in total has appeared in my n trials, and then times 1 and minus P, and minus the x. So the number of times tail appeared. So this is the likelihood. Then you optimize this likelihood by maximize it and looking for the best P, right? How do you do it? You take a log, and then this is what you get. And how do you maximize this? How do you maximize this? How do you maximize a function? You take a gradient, you set it to 0. So in this case, take a derivative versus P. You set it to 0, which is next page. And every step is there. You take a derivative versus P, and this is what you get. Hopefully you still remember how to take a derivative of log function. Okay. And this is you get the derivative, you set it to 0, and then just with simple verification, you're going to get this equation, and then this equation, and you get the best P is number of times head appear over the number of times you flip the coin. So even though we always use P over N, but this gives you a solid proof. Why? Because it maximizes the data likelihood. Okay, so feel free to read it. So it's very easy to prove this. Everything is included. All right, so now how do you estimate for a specific word, condition on a specific class? And you just do fraction of the document of label CJ in which word I appears. So those documents has the W and their label is CJ on the denominator. In the denominator is the number of documents in your training data. And then when there's a new document coming in the testing state, how do you do it? So you should also know this very clear. It's really a lookup operation, right? The 10th example is exactly the same as this, but a little bit more complicated because in the 10th example, each variable, it's not just binary. There are also choices, maybe 3 possible choices. In this case, there's only 2. So that's why you have only 1 parameter, and the other case it's just 1 minus the p. So it's a simpler case. Okay, so but that's not enough. So you know the training, you know the testing, but it's actually not enough at all. You can just do perform this calculation, and I actually talked to you about it. When you have a lot of words, that joint probability is many smaller number, small positive number multiplied together. And this easily have the overflow problems, the numerical problems. And you can't, it's just not stable at all. So that's why, in fact, what we truly calculating is not PC times, so what we're doing is not actually the previous page. It's not this page at all. What we're truly calculating is actually this page. It's every number needs to have a log there to make sure it's numerical stable. The summation of logs, to avoid this numerical problem. And then you just do argmax. The reason why you can do log is because log is a monotone function, right? It doesn't change the argmax result at all when you're performing a monotonic function on each entries of the comparison.
Great. So this is the end of this module. See you in next module.